Hello, and I would like to perform the intuition video for electric current. So what is electric current? This is for a calculus-based Physics 2 class, and the idea of electric current is the following, that electrons can be moving in time, and as a result, this should be studied. So what do I have here? I have an electron that is moving around somewhat randomly, and what I can do is I can reset it to the center position, and then I can also set up an electric field. Now let's talk about the various parts of this. So an electron that is set up in a conductor moves around somewhat randomly, like molecules do in an ideal gas. So if you are familiar with ideal gases, the molecules move around in a somewhat random fashion due to temperature fluctuations. What we see, if you look at this electron over time, that it moves around somewhat randomly. Now it seemed like this particular one went to the right, and it's sort of staying to the right, but it's definitely moving left and right somewhat randomly. That's because there's no electric field imposed on it. If I reset it, you might see it move left, you might see it move right, but in general it does not move very far. It usually stays more or less in its position. Now it moves around somewhat randomly. Okay? So that's the basic idea of a charge when there's no electric field. Okay? So every time that I do this, you'll see the charge moves around somewhat randomly. Okay? Now, the question is, what if I quickly reset it and then impose an electric field? And let's suppose the electric field is positive. So let's reset and impose an electric field. Let's say the electric field is to the right. Now, if it was a positive charge, an electric field to the right would cause the positive charge to be pushed to the right. But that also means a negative charge should be pushed to the left. This is an important distinction. That is to say, remember Benjamin Franklin thought that charge was positive charges. In other words, electricity. He called electricity electric fire, and hence it's usually termed with red and a plus charge. We now know in 99% of charge motion, it's actually electrons that are moving. Remember, electrons are on the outer shells of atoms, and then furthermore, electrons are much smaller mass and they're much more likely to transfer. So when there is an electric field, let's say to the right, then an electron would feel an electric force that's in the opposite direction of the electric field, and that should move it to the left. Now also, this would be true if it was vice versa, an electron would move to the right. Now, notice that an electron, when it moves around, it still moves around as if it's in an ideal gas, but it has a preferred direction. In other words, if the electric field is to the right, then the electron prefers to move to the left. If the electric field is to the left, the electron prefers to move to the right. Now, the reason I bring all this up is for the following reason. It's because this notion of setting up an electric field is what gives rise to electric current. It turns out that charges move in a conductor in a somewhat random way, but still a somewhat preferred direction. Remember, if there's no electric field, you'll usually see in these random simulations, there's no real preferred direction that the electron actually moves. However, if there is an electric field, you'll see that there will be a preferred direction that the charge moves. If the electric field's to the right, the negative charge will tend to move towards the left. And this is a manifestation of, even though there's still random motions like an ideal gas of a charge, you could say that the preferred motion direction has to do with the electric field that's set up. So we have to set up an electric field to generate an electric current, which is the movement of charge. Now, what we have here is a simple electric circuit that we can make modifications to. Let's ignore these light bulbs that are currently disconnected and not part of the original circuit that we're going to study here. So what do we have? We have a battery, which I will discuss here in just a moment. We have a switch, we have a switch, and we also have a light bulb, okay? And we can control the values of each of those. So if I look at the values, notice that the battery has units of voltage. That's the SI unit for electric potential. Well, remember, that is electric potential energy per unit charge. This is what voltage really is. So think of the battery as being an potential energy per each charge. So volts is joules per coulomb. Notice that each of these light bulbs has units of ohms, and that's because it's a resistance. Think of resistance as the inhibiting of electric current, and that is inhibiting charge motion. The greater the resistance, the less the current by what we call Ohm's law. Because if we have a constant voltage source, V, then the greater the R, the greater the resistance, the less the current. So notice that V divided by R equals I. Voltage divided by the resistance is equal to electric current. Well, let's see what happens if we close the switch. Now notice, this closed switch, this switch right now is in the open position, but let's go ahead and close the switch. So when the switch is closed, we now have a continuous electric circuit. Now notice a few things. First of all, when the switch was open, the resistance was infinite, or nearly infinite. That's because air is a very, very, very weak conductor. This we assume to be something like copper wire. This is the most common conductor you'll see used in practice worldwide as per the year of this recording, 2020. Notice copper is not the best known conductor, but it's relatively efficient, and it's also relatively inexpensive to mass produce. So you see the color represents copper, and we're looking at the motion of charge as if it's conducting electrons, but we know that real wires, when we actually install them, will be typically insulated for safety of the user. Notice the switch being in the open position does not allow electric current. In other words, does not allow charge to flow because the resistance is nearly infinite. But when the switch is closed, notice that closed allows for a continuous circuit, that is a continuous path for charge motion, and notice that this switch has nearly zero resistance. In fact, for the sake of this course and for most basic electric calculations, wires are assumed to have zero electrical resistance. Now, zero electrical resistance is not a perfect assumption, but even most modern wires have very small amounts of electrical resistance, if not over a very large distance. In other words, only when we transmit electricity over very large distances, like electrical transmission power lines and very long wires, is there power loss due to the length that we transmit the electricity over. So, it's not a perfect assumption to assume that wires are without wires are without resistance, but it's a good enough assumption for our purposes. Okay. Then let's also discuss what the brightness of this light bulb means. The brightness is indicative of the power dissipated. Now in this case, the power delivered by the battery will be exactly equal to the power dissipated in this resistor. That's because there's only a single resistor. If in fact I was to remove this resistor, the current would be nearly infinite. That's because there would be no resistance, and this current would be extremely large. The battery would get way too hot. We would probably cause a fire. In fact, I think we can see that simulated. By the way, do not try this at home, but notice that the electric current is extremely large and just outside of physical values. So let's go ahead and stop that. Okay? So let's go ahead and reconnect this bulb, and lo and behold, it lights. So the lighting of the bulb is indicative of electric potential energy, that is voltage, being transferred into a different form, that is electromagnetic energy, namely light. Now, this is an incandescent light bulb, so think about light bulbs that were used for many years from the, let's say, 1950s through the middle 2000s, most places around the world. These bulbs also would transfer a lot of energy also into heat, not just light. So the bulbs themselves would get quite hot. Now, in the 2000s, many of these incandescent bulbs have been replaced with either complex fluorescent bulbs or maybe even LEDs, which are light-emitting diodes. I won't be discussing all the details of complex fluorescent bulbs and light-emitting diodes, but suffice it to say, they are generally more energy efficient, and they use a different process of producing electromagnetic radiation compared to an incandescent bulb. An incandescent bulb has a very, very thin filament that when the charge is forced through that very, very thin filament, usually a material like tungsten, the filament gets quite hot, and it gets so hot that it actually glows. When the temperature is really high, it glows because it's at a very high temperature. So it'll glow with its temperature, several thousand degrees Celsius, and that actually gives off white light. Okay, so this is the idea of a light bulb, that is especially an incandescent bulb. Now notice, these are physical devices. This looks like a Duracell copper top battery, if you like. This looks like an incandescent light bulb. But remember, an incandescent light bulb, we know that to be an electrical resistor. So again, resistor is resists electric current flow. In fact, we should see the same results if I take this bulb out of the circuit and then instead replace it with an electrical resistor, which I set to the same resistance that was the bulb. The only thing that's different here is that this resistor is just some resistor setting. We don't necessarily see how the energy is being transferred. In fact, this resistor might be getting warm, but we don't really know how the electric energy is being dissipated. So this is a resistor you might buy as part of a hobby kit if you're working on electric circuits, or if you're closely setting the resistance in an electric circuit. Okay, so let's go ahead and take this resistor out. By the way, these resistors have very particular settings, that is, very particular values of resistance associated with these colored bands. Those colored bands indicate how large the resistance of this resistor is. Notice as I increase the resistance slowly from 6 to 7 and 8 and then 10 and then 11, 12, and so on, ohms, notice that the colors on the bands change. And that's because, depending upon what the resistance is, there's color information about multipliers and digits and so on. Now, I am not skilled, as the person making this video, to know what all of these colors mean on a resistor, but suffice it to say there are standards and there are tables where you can look this up if you need to know what the codes in terms of these colored bands are for resistors. Okay, fine. So let's remove this resistor, and now let's go back to a bulb. Okay, so this is what we had before, and notice that this is, again, a physical setup. These are physical devices. Notice also that the conduction electrons, that is, the electrons that are actually being transferred, seem to move in this particular electric circuit clockwise orientation. That's because those negative charges are coming off the negative terminal of the battery, which in this case is the voltage source. We're assuming it to be a constant voltage source. Let's assume this is on for such a short time that the voltage of the battery does not decrease. Notice that if the electrons are going to move clockwise, that is actually opposite of how electric circuit problems are often calculated, at least mathematically. Usually, the standard is to use what is called conventional current, and the convention follows the Benjamin Franklin standard. Again, remember, Dr. Franklin thought that electricity was positive charges, was electric fire. And the idea is that retaining that convention, conventional current, we assume positive charge comes off the positive terminal of the battery. So if I go over here and switch to conventional current, notice that conventional current will have the charges move the same rate, but assume that positive charges come off the positive terminal of the battery. And instead of negative charges moving clockwise, positive charges move counterclockwise, because it's not only the opposite charge sign, it's also the opposite direction, which is still mathematically the same amount of charge delivered. Because negative charges that move left from the battery is the same thing as positive charges that move right from the battery. So minus times minus is the same thing as plus times plus. Hopefully you understand the sign, SIGN, convention. Okay, now one more thing. These physical devices are not usually often shown to be the devices that you would sketch in a diagram. In fact, it takes a long time to sketch these physical devices. So what is often rather used is called a circuit diagram. And a circuit diagram shows the electric current and shows the devices along with the wires. In fact, let me open the switch and take off the values so that you can see these devices a little better. Notice this is the standard symbol for an electric bulb. Notice that these are disconnected bulbs. Notice this symbol right here is the symbol for a constant voltage source, usually a battery. Notice that bulbs have sort of a two different sides, whereas a battery has a long line and a short line. The long line is a positive charge, the short line is a negative charge, that is the polarity of the battery. Some battery symbols are two long lines and two short lines, but in either case, the long line side indicates the positive terminal of the battery. Also note, this is the symbol for a switch. Notice this is the switch in the open position because there's a break in the line, but notice that there's spots where a connection could be made. And then when the switch is closed, that's a closed switch. So it just looks like a straight piece of wire. Straight pieces of black is just going to be wire. And then again, for the sake of this class and for many beginner electricity calculations, assume that wires are resistance free. Okay, so this is the basics of electric circuit. One more thing I should say, and that is, how do we calculate electric current? So I went over this briefly before, but let's say this again. So imagine that we have a 12-volt battery and a 6-ohm resistor. We should be able to calculate 2.0 amperes in this case. because 12 volts divided by 6 ohms is 2.0 amperes from Ohm's law. Notice that if we open the switch and we break this portion of the line, and then we install an ammeter is a device that measures electric current. Now, some people call this amperage, but that's not quite the right term. Sometimes it's called amperage just because voltage has units of volts. People think that amperage has units of amperes. But really, the physical quantity is called electric current. So the charges are going to move through this ammeter, and they should hopefully show 2.0 amperes. And that is indeed what they show. Whether we show the circuit diagram or the physical devices, or if we show the conventional current or the electrons moving through the device. Notice if we open the switch, there is no electric current because there's no path for the charge to flow. Furthermore, suppose we increase the resistance to 10 ohms. So from Ohm's law, we know that voltage divided by resistance is current. So 12 volts divided by 10 ohms should be 1.20 amperes. And that is indeed what we see. Notice a couple things also, that the charge moves slower when there's less electric current. Think of electric current as the delivery rate of charge per time. It's actually closely related to charge velocity. So the definition of electric current is the change in charge over the change in time. Furthermore, do you see that the light bulb also looks dimmer? That's also to be expected, because if there's less electric current, the charge is not being pushed through the light bulb as quickly, and the light bulb will dissipate less energy. Okay? In fact, power delivered by a battery is going to be like current times voltage, I times V. Notice that if I is less, because resistance is greater, then the power delivered by the battery is less, so the power dissipated by the resistor is also less. Okay. I think this ends the introduction to electric current and electrical resistors tutorial. I'd like to thank you for your attention, and I'd ask you to please subscribe to this channel. Please smash that like button if you enjoyed this video and give it a thumbs up. Please share the video, and I will see you in the next video. Thank you for your attention.